All right, shall I kick it off now? Very good evening, everyone. Thank you very much for coming to the No Jargon Talks. We have two amazing speakers today, Doris Lee and Jared Hand. Before I give a brief introduction about them, Lorena is going to walk us over some community guidelines. So over to you, Lorena.
Yes. Okay, since this is put on by women and minorities in physics, we have guidelines that we use during our meetings, and we want to stick to the same community guidelines in these talks as well. So I have the document here that I'm sharing. I'll post this in the Zoom chat as well, but I quickly want to just read like the key points of our guidelines. So these are things we want you to keep in mind during any discussion. And if you notice that someone is not acting in accordance with these guidelines in a way that is hurtful or counterproductive to discussion, you can message one of the moderators. So you can message me or Yasha today and let us know if something happened. Okay, so first, never assume someone's experience, viewpoint, or perspective. Practice being non-judgmental, focus on the facts of the discussion or situation without evaluating them as good or bad. Consider practicing acceptance. Try to think dialectically. So that is the idea of both and instead of either or. So like try not to do black and white thinking. Two things can happen or exist at once. And then finally, just be mindful about how much time you're taking up as you're speaking. We're sharing the discussion, and let's try to keep things within like the realm of what we're talking about here today. If there is something you want to discuss further, we can put you in touch with one of the speakers afterwards. Okay, so I'll post this in the chat, and now, Yasha, you can continue.
Awesome. Thank you, Lorena, for sharing the guidelines. We are also going to use this very cool app for people to ask questions. In case you don't want to put this in the chat here, you can just click on this link I'm just sharing in the chat and post your question there after the speaker's talk is over, and we will just convey this question to the speakers here, and you will get your answers. Always feel free to unmute yourself and ask questions if you feel like doing that. You're most welcome to do it. Let's get started with Doris's talk. Doris is a graduate student in the Department of Physics and Astronomy at the University of Pittsburgh. Her research focuses on how to improve students' motivational beliefs and physics learning in introductory and advanced physics courses. She also has made a very cool website recently, which I'm going to share in the chat box here. I would encourage people to go and check it out to see more details about her research. And it's all over to you, Doris, now.
Thank you very much, Yasha and Lorena. And let me share my screen. Okay. So can you all see the screen?
Yep.
Okay, thank you very much. Hello, everyone. I'm Doris, and I'm very happy to have this opportunity to talk about some studies about students' motivational beliefs in physics courses. In particular, based on these research findings, I will talk about how to build an inclusive and equitable learning environment in physics as instructors, TAs, and as students. So before I start, I would like to share like two photos. The first one is a very famous one. I believe many of you have seen this before. And this is from a physics conference 100 years ago. And these people are almost the most famous physicists in the world. As we can see, we can find there like Einstein, Dirac, and Schrödinger. However, we also notice that most of these people are men, and there is only one woman in this picture, Marie Curie. And another photo I would like to share is this one. This is another physics conference 100 years later, but we still realize that there's no much of difference. Female are still underrepresented in physics. So the issue of underrepresentation of women have been studied by many researchers, and researchers focused on several aspects. Like first is how students' prior preparation influence their learning and their retention in physics. In addition, how about teaching methods influence students' learning and whether they choose major in physics or other STEM disciplines. Another very important factor is students' motivational beliefs, including students' interest, their sense of belonging, and whether they believe they can do well in physics. All these motivational beliefs are also very important for students, not only in their performance, but also engagement and the retention and their choices of major and careers. So today I would like to talk about some studies in students' motivational beliefs. The first motivational belief I would like to introduce is self-efficacy. So the definition of self-efficacy is one's belief in one's ability to succeed in a specific situation or accomplish a task. In physics, is students believe about whether they can do well in physics. And the study I want to show here is we compare men and women self-efficacy in physics 1 and physics 2. These are two calculus-based introductory physics courses. And in particular, we compared men and women with different performance. Like if you can say the horizontal axis is the grade. So we compare men and women with grade A, with grade B, and with grade C. As we can see in both physics courses, female students have lower self-efficacy than male students. In particular, if we look at the physics 2, we can see female students with a grade A actually has a similar self-efficacy as male students with C grades. That means in general, female students may feel low, have lower confidence about their belief, about their ability in doing well in physics than their equally performed male students. So actually this can partially explain why female students feel hesitant to choose major in physics or other STEM disciplines. But to deeper understand why this happened, we may need to get more information. So we may look at some interviews we have done with female students in our course. So the first female student said, some people have just a natural ability for physics, and as hard as I work, maybe I can become okay and can do those problems well enough and have adequate grade on exam, but I don't know if I can truly become fluent in it. Some people just have the natural talent for physics, but I can never do what they do. Another female student shared that I don't feel comfortable in this class. Physics gives me a sinking feeling. It kind of scares me. I compare myself to other people. It feels like I do not belong in this physics course. According to these two interview quotes, we can find both of them mention something like people need natural ability to do well, and people around me are very smart, and I don't think I can do. I do not have this natural ability, and I don't feel I belong in this atmosphere or this learning environment. So these points are related to the next two motivational beliefs I would like to talk. The first one is students' sense of belonging. Another one is the view of intelligence, or we can call it mindset. If people think the ability or their talents about physics can be developed, or if they put more effort, they can improve their ability to do physics, then they have the growth mindset. Otherwise, if they think if you are good at it, you are good at it. If you're not, you will not improve. Then they have the fixed mindset. And according to the studies and the interviews, we found female students are likely to have low sense of belonging, and they may also have fixed mindset in some level. We may dig deeper to understand why this happened, because there's still some interview quotes, but we do not know what caused this results, this phenomena. The major thing I would like to mention here is a stereotype threat. So the societal stereotypes and the biases about who belongs in physics and who can do well in physics can actually influence students' motivational beliefs. And they will have lack of encouragement and recognition. For example, in a study, researchers find in a museum, parents are 3 times more likely to explain science to their boys than their girls. And in addition, in the interviews we found with our students, some female students reported that in their physics courses, the instructors are more likely to praise male students than female students. And some female students also reported that in a group learning environment, especially when she was the only female student in the learning group, sometimes her contributions and ideas are ignored by other male peers. And this kind of experiences can really influence their motivational beliefs as well as their performance. As a result, underrepresented students in the society as a whole have a higher tendency to associate poor performance of underrepresented students with lack of ability. And if a student from underrepresented group didn't do very well in an exam or a quiz, they may think, oh, I'm not good at this. Why should I even bother this? What's the use in trying if people like me are not likely to be successful? And if students think about this stuff when they are doing homework or exams, it's likely to influence their performance because the awareness of stereotypes is taxing and takes cognitive resources. Like people cannot focus on many different things at the same time, and it will hurt their performance. And the poor performance will reinforce their stereotype in their mind, right? So it's like a very negative feedback loop. But our question is how to break this cycle. And especially, I would like to share some experiments and intervention researchers have done on students' sense of belonging and their mindset or view of intelligence. The first one is sense of belonging intervention. Actually, this work is already done in at Pitt, and in the first year, first semester of students' first year in college, they will be divided into 2 groups, and the first group is intervention group, and the second group is control group. So for the control group, we didn't do a lot for control group, but for intervention group, there will be a graduate student coming to the class, the first recitation class in their first semester in college. And the graduate students will share some of their own experiences in the first year, first semester when they was in the first class. And the students will be taught that it can be easy to feel overwhelmed or sometimes wonder to yourself, do I really belong here? And this kind of feelings are very normal, and many people have this kind of feelings, and you are not alone. And after this, student will be asked to write something on their own about some of their own concerns about college, and how do you think these concerns will change over time? After this writing activity, students will listen to quotes from the graduating seniors. And these quotes are selected focusing on how the senior students overcome the challenges and the difficulties they have at the beginning of the college studies. After this, students will discuss with each other about these quotes and the things they have written. And this is the intervention group, and we didn't do this for the control group. We measure the students' performance at the end of the course, and for the intervention group and the control group. And here is the result. We find in the control group, there are statistically significant gender differences in students' academic course grades, average course grade. However, in the intervention group, this gender differences is not there anymore. So this study, this intervention actually show that students' motivational beliefs, like their sense of belonging and whether they feel comfortable in the first year, do they think they are alone, or do they think everyone have this kind of feeling, can really influence their performance. And the main message we want to convey through this intervention is the difficulties are normal and everyone have this kind of difficulties, and you are not alone, and it can be overcome, and it can be improved if you like put more effort in this. It's not permanent, it can be changed. So this is a study about sense of belonging. The next one I would like to share is about mindset. So this is a study, actually like experiments on students from 10 to 12 years old children. And there are 3 stages of this experiment. In the first stage, those group of students will be given a set of questions, and they are not very hard, so they are moderately difficult problems. And when they solve these problems, or when they do finish these things, most of them will do very well because these questions are not difficult. And they will be divided into 3 groups. In the first group, the teachers will praise these students with the neutral way of praising. Like they will say, wow, you did very well in these problems. You got how many right? And that's a very high score. And another group, in the second group, students will get the intelligence praise, which is the first part is the same, like you did very well. However, the teacher will also say that you must be smart at these problems. So this is the intelligence praise. For the last group, the effort group, students will get, well, you did very well, and you must have worked hard on these problems. So after they got this praise from teachers, they will do the second set of questions. And this set of questions are much harder than the stage 1s. And most of them didn't do well in the stage 2. So after stage 2, they will be given the last set of questions. And in stage 3, they will be given the same level difficulties question as they had in stage 1. However, the question themselves are totally different, but they have the similar difficulty level as in stage 1. So the question people want to ask is, do you expect any difference in performance between the different groups of students on stage 3 problems? And here I just show the result. As we can see in this figure, students who got the neutral praise actually did very similar in trail 1 and in trail 3, because first they have the similar difficulty level, and the students in the neutral praise group just get a very regular praise. However, for students who got the intelligence praise, like you did very well, you're smart, you're intelligent for doing this, they actually had the lower performance after a failure, because remember, in the stage 2, students get very hard questions, and actually for some people they might be feel they are fail in this stage 2. After stage 2, and they get the similar difficult level questions, but they perform the worse in stage 3. And they ask to do easier problems in the future because they are afraid of doing like difficult question after stage 2, and after they got the praise for their intelligence. However, for the last group, the effort group, students actually performed better and asked to do more challenges problems in the future. So according to this experiment, we can say whether students think the study as as a process that as focus on the process, focus on learning, or focus on the learning results, the performance can really make the difference on their performance and on whether they want to do more challenges problem in the future. So this is the difference about students' fixed mindset and the growth mindset. The last thing I would like to share is it's also important for instructors or TA to have a growth mindset, because according to this study, students performed poorly in courses taught by faculty who had fixed mindset. For example, if we compare the fixed mindset group and the growth mindset group, for faculty who had a growth mindset, students in their courses actually performed better. And students in the fixed mindset group, like a student who had who are in the fixed faculty who have the fixed mindset, actually has larger difference, like the racial achievement gap in the course. So if we compare the achievement from between white Asian students and the underrepresented students under like minority racial and ethnic groups, we can see the differences in their achievement are larger than the students, the gap in the growth mindset group. So as a summary, I would like to share that for students, actually, if we want to help to improve the learning environment, we can focus on our efforts rather than intelligence. And actually we can see we can grow our intelligence, and the struggling is normal thing, and it can be overcome, and it's temporary. And we also can compare ourselves on our own personal growth rather than compare with other people. Other people are very smart. We do not have to do that. And we need to study in a group, because we can communicate our experiences with others, and then we'll not feel we are alone. And for TAs and instructors, we should praise our students' efforts rather than their intelligence, and we should recognize our students in appropriate way. So we do not want to say some question is very easy, because for them they might be hard, and we do not want to hurt them and let them feel they are not good at it. And we also need to develop a good growth mindset, not for our students, but for ourselves. So this is all I want to share today. And thank you very much for being here. And I would like to take any questions and comments. Thank you.
Thank you so much, Doris. That was a really amazing and engaging talk, I would say.
Thank you so much. I was a little nervous, sorry.
No, it went really well. It was pretty interesting. We have a question for you. So about the self-efficacy and grades chart, do you think men are overconfident or women are underconfident?
Let me go back to that slide.
Yeah, the self-efficacy and grades chart.
For this, I don't think men are in this level. I don't think they are overconfident, because I believe everyone should be confident about I can do well in physics. I can, if I put hard work, I can improve. So I think female students have lower confidence here. This is what we want to improve, and we don't want to tell male students you should not be that confident, right? We want everyone to be confident. Actually, there are some studies about students' self-efficacy, and their belief if there are some intervention. So people find the intervention are really helpful for female students who have lower self-efficacy or who have stronger stereotype threats. Like if they have lower self-efficacy, the intervention are more likely to improve them, improve their self-efficacy, motivational beliefs, and the performance. So if they already have high confidence, already have high self-efficacy as their male peers, this intervention are not as helpful as them because they already have high. So my thought on this is actually female students performed very well. They deserve to have the same confidence as their male peers. And as instructors or TA, we need to help them to develop because they should have. But for the current learning environment, because there are so many stereotypes and threats, and for example, the example I gave, like in the learning group, sometimes they are ignored, and their parents and instructors may not have the encouragement and recognition. They cannot develop the confidence they should have. So this is my thought on this. Thank you.
That makes sense. I have a quick question because we are already on this slide. So what I see here is this study is kind of old. I think this is a plot from 1977 paper.
Yeah.
Am I right?
Yeah, that's right.
So this is conducted based on 2 gender groups, male and female. Have you seen any recent study which has been conducted including the gender groups which are not just male and female and the others as well?
This study is conducted at Pitt. So I haven't checked for like other universities. At Pitt, we always so far we used the gender information collected by university, and the university used the binary like measurement. But we recognize there are not only 2 choices. But for the current study in our group, we used this binary, and I'm looking forward, and I think we can do more about this and to include more gender groups.
Nice, awesome. We have one question from David. You can go ahead and unmute yourself.
Hi, David.
Hi, Doris. Really great job.
Thank you so much.
So I was wondering also about this plot here, and sort of this finding, right, is like it's specific to this one university setting, right? Like this one sort of distribution. But I was wondering if you know about any studies that people have done that sort of control for the gender of the instructor or like the gender distribution of the department, right? Like I would imagine that maybe in a department where there are more like prominent women professors or something like that, right? Where there's sort of like higher gender balance, that this disparity would start to shrink. And I'm wondering if that's something that anybody has quantified, if you know of.
Oh, okay. I think so. Are you asking how about the faculty are female? Will this help?
Yeah, like does the presence of like a woman as the instructor increase the sort of perceived confidence of women in the class, or is this sort of a class result?
I see. So for our study, because this is study in our group, we checked the effect of instructors. Like we have 4 to 5 instructors each year, or around 4, and we didn't find like there are any instructor level effects. However, we only have 1 female faculty, so we didn't have enough sample size to check whether the female faculty make a lot of difference. But for the instructor level, between different instructors, we didn't find the significant difference. However, according to the interview we have done, some females, so most of female students mentioned that they felt comfortable in a course taught by male faculties. It's fine. There's no significant difference for them. They didn't think like female students are always better than male students for female students. It's really depend on faculties themselves. And they also give some examples about how female faculties says, oh, this question is so easy, and even elementary students can do that. So it's not only for male faculty. Another study I learned from another university is the last study I showed, the fixed mindset, that study. So for faculty who had the fixed mindset, the students in their groups performed worse, and actually the difference between different racial ethnic groups actually larger than the course taught by growth mindset faculty. And that study is, the result is like that, regardless of the faculty's gender and background and their position. So I haven't unchecked whether this similar kind of study in this slides have done in other universities or with different gender of faculties. But my thought on this is maybe the most important factor is faculty's mindset and their own motivational beliefs. Gender maybe is not the direct predictor of this.
Cool. Awesome. Thank you so much. I appreciate it.
Thank you.
Very cool, Doris. Hope this answers everybody's question. We have 2 more questions in the poll, which I'm going to paste in the chat box, and you can take your time, Doris, to answer those questions.
Okay.
Because of time constraints, we will move on to our next speaker. I would like to introduce Jared Han to you guys. He's a 4th-year graduate student in the Department of Physics and Astronomy at the University of Pittsburgh. His research focuses on type 1a supernovae, and he works with Professor Michael Woodbasey, and he loves battleships. So all yours, Jared.
Okay, so I'm going to go ahead and share, but if I look awkward staring at a 60-degree angle away from you guys, I apologize. It's just the way this, I think, is gonna.
That's totally fine.
Yeah, just fair warning. All right, you guys see my thing?
Yep.
All right, so I already want to say that you should lower your expectations because Doris has objectively blown this presentation I'm about to give out of the water with hers. But it's more of an applied physics and kind of an applied ballistics. Anyone that's taken a physics class has ran into an issue where you have to figure out how far an object goes once it's thrown in the air or something like that. And to an extent, that's what this presentation is about. So this is a picture from the Battle of Jutland, although it's Jutland by Anglo-American speakers, of well, they're battle cruisers, but they're effectively battleships for our intents and purposes. But one is exploding after being hit from a distance of about 10 kilometers from an 11-inch shell. So when I say 11-inch shell, I mean 11 inches in diameter. And there's another ship that's the same size as the one that exploded just forward with shell splashes showing how large these splashes are. So real quick, we should probably talk about what a battleship is. Frequently we see in the news like, oh, new battleship has been commissioned. Is this the new battleship coming from Britain or China or the US? So they're not aircraft carriers, which is an easy thing to differentiate. This is a World War II era aircraft carrier. And that's kind of, there's airplanes on it and carries airplanes. There's also smaller ships. This is a destroyer, which is used for escorting bigger ships, such as aircraft carriers or battleships. And it does have guns. It has other things on it, but its main weapons are guns. There's also these things called cruisers. It's kind of a weird name from historical reasons, but the idea is it cruises around independently of the fleet. Although by the time World War II came around, that's not really what they were doing. And as you can see, it has more guns and they're bigger, and the ship is bigger. But then there's battleships. And so this is a famous battleship, the HMS, the IJN Yamato, which is the heaviest battleship ever built. And just to give an idea of scale, there's some people on it, but there's also this little turret, which is turret is what houses the guns. And this is what would show up on a cruiser. And this big turret, which has these 3 massive 18-inch guns, weighs as much, actually it weighs more than the destroyer in the picture. So just an idea of the scale of these vessels, where they were massive, they were overly expensive, and they bankrupted countries when they would build them. And so making sure your battleship was firing accurately at range was important. And so that's where fire control came into play. And so the idea here is that ballistics is a study of how an object with a shape travels through the air after it's given some initial speed and direction. And that speed and its mass gives it some amount of energy. And there's 3 types of ballistics that are of interest to the warmongering folk, or people who do distance shooting, I guess. There's interior ballistics, or the ballistics occurring in the barrel of the gun. There's exterior, which is while it's traveling through the air, the shell. By this point, when you start getting into large caliber, they refer to them as shells and not bullets. And then there's terminal, which is what happens when you hit the target. But fire control pertains to exterior ballistics and figuring out how to get the target from the barrel, or get the bullet from the barrel to the target as accurately as you can. And this is a picture of the USS Idaho bombarding Okinawa at borderline point blank range. And you can actually see the shell coming out of the gun. And so an idea of how big these shells were. So this is the USS Iowa. This guy is standing in front of a capped and uncapped version of these armor-piercing shells. And here, all these little cloth bags are bags of powder, of gunpowder used to propel these shells. And when I talk about these shells being heavy, I mean, like, they weigh more than this. This is a Ford Fiesta. And so the Iowa class battleships, the last battleships built by the US, which is what most of the plots I'll be showing, or plots or diagrams are based off of, had 9 of these guns that could fire 6 of these 16-inch shells. It could fire 2 a minute per gun. So that means it could fire 18 of these cars at a target up to 42,000 yards away, which is like 38 miles or something like that. So pretty extreme. But the idea here is that we got to take into account gravity. And so if we dumb this down to what a physicist would try to study, it's the ideal situation where we ignore the effects of air and we only look at the effects of gravity. And so what's neat here is some interesting things. If we ignore the ships moving, which makes things much more complicated, you get some nice symmetries. And this is actually from a fire control manual for enlistees in the US Navy from 1951. That's why it looks the way it does. But as you can see, there's this interesting symmetry where the range, the highest travel point of the round is halfway to the target. And that means that the firing angle is the same as the incoming angle. And this is due to that mass basically not being important. Well, that's part of the reason. And so basically in order to figure out what you're hitting, a stationary target from your stationary battleship in a vacuum, is you just need to know the initial speed and the initial angle of your round, and you'll always hit the same target. The initial speed is what determines the energy that allows for travel that distance. And here's some other interesting situations where there's actually there's 2 elevations you can use to get to the same place with your rounds. And so, for example, if you want a short range, you can either point your barrel all the way up, very high parabolic plunging fire, or you can have a direct fire up here. And so this is just showing another one of these interesting symmetries. As you go up to 90 degrees, you start having what a physicist or mathematician would be like. You have two mathematical solutions to this, I guess, solving for your zeros. But in reality, we have air resistance. So air resistance is like friction. A shell, as it's going through the air, is colliding with the air, which is made up of oxygen particles, water vapor, all sorts of stuff. And as it's hitting that air, which you can think of as just static right now, the air is getting pushed away and is basically converting is transferring some of its energy and momentum to the shell as it moves, thus heating the shell up and slowing it down. And so as a result, you don't get as far. And how far you get, given an initial speed and angle, is now dependent upon both the shape of the shell and, more importantly in this case, the mass of the shell. And so that's why the gun size is important. The 16-inch shell can get so much farther than, say, a 5-inch shell or a 1.1-inch shell, simply because it has more energy that the air would have to beat back as it travels to its target. And so the maximum range is 42,000 yards, which I meant to look up like a real world scenario, like a real world thing, but like that'd be like shooting from the edge of Pittsburgh to the other edge. So pretty far. And so they also show, like, if there was no air resistance, the shell would go pretty far. Oh, actually, I thought I had one more thing. And real quick, see how these trajectories are no longer, there we go. Sorry, are no longer symmetric. It starts falling faster and faster as it goes because it's losing energy. It's losing speed because it's losing energy. The other thing about air resistance is that it's dependent upon the speed of the object. As the object starts slowing down, the air resistance decreases. Now, another interesting thing to take into account, the ship is rolling side to side and back and forth, up and down in the water. So while they're trying to shoot at a target that's 10 miles away, 15 miles away, 20, you have to take into account your ship going back and forth and rolling around. So they have instruments to do this. And you have to take into account the movement of the other ship, because at maximum range, it can take the shells are in the air for 90 seconds. So a minute and a half. And so the ship can then turn, the enemy ship can turn, move forward, slow down, speed up. And so all these things have to be fed in, have to either be calculated each time you shoot the gun by hand, which is not possible, or you use crazy computers. But there's a few other things that this computer will have to take into account. The wind and the earth. So this air you're shooting through is not stagnant air. It's moving. There's wind. And so this wind requires what are called windage corrections. And so this is important even if you're shooting a rifle at the range. And you have to take into account the wind pushing on or slowing down, pushing the shell as it travels. And the wind is also dependent upon the altitude. So you have to take into account that. My personal favorite thing is that if you don't take into account, these shells fire so far that if you don't take into account the curvature of the earth, you would always overshoot at anything other than what's called point blank range, which is effectively if you can do if a Taylor expansion of all this process is accurate. You don't have to take into account like air resistance or anything because you just hit your target just aiming downrange. So this is clear evidence that the earth is not flat, or else battleships wouldn't be able to engage other battleships. The other thing is the earth, while the shell is going through the air, the earth is rotating underneath it. And so you have to take that into account because not only because the ship that you're shooting at is itself moving on the earth while the earth itself is moving, you have to take into account that difference whenever you're shooting north to south or south to north. And this is the Coriolis effect. So all these things need to be accounted for in these big fancy computers. Now, this is back when there were no digital computers. They were all analog computers. And so here's an example of the Ford Mark I ballistic analog computer, which I hope is more reliable than Ford's nowadays. But there would be a group of guys that would sit in here, and this device is entirely analog and mechanical. So it would do these integrals or addition or subtraction using the physical devices like gear ratios or like a ball on a cylinder on a plane. I don't know how that works, but they figured that out in the 1800s, and they did integrals with it. And then you had all these different radar setups that would find out where the enemy target is and then figure out how to fire at it and track it and fire at it. And that's what these are from the USS Iowa, which is a battleship you can visit in Los Angeles. There's two of their two radar pieces that you can see. The one on the left is for the smaller 5-inch guns. And then there's the one on top of this little tower, which is actually meant for directing the 16-inch guns, which are the big main guns. Now, how effective were these analog computers? So this is actually a picture of the USS Washington firing at the Ijan Kirishima at the Second Naval Battle of Guadalcanal during World War II. So the Second Naval Battle of Guadalcanal was one of 2 times that battleships fought each other during the Pacific theater of World War II. And it was fought not too long after Pearl Harbor, just to kind of give an idea of time. And during that battle, the USS Washington at about 7 miles, so 8,400 yards, fired 75 rounds of 16-inch shells and with 9 confirmed hits. So that's basically looking at the other ship and hitting it with 9 cars. And so that's a 12% accuracy rate, which you're like, okay, that's not great. But now let's ignore having the computers. And so this was also at night. Now let's ignore having the computers in the Battle of Jutland, or Jutland, if you don't care about how languages work in other places. Then what you end up with is a 3% accuracy with ranges varying up to 15,000 yards, but fought in the middle of the day. And this was during World War I, fought in 1916. So before they had these analog computers, what they did is they figured out the distance using these range finders, which would adjust, just like how our eyes have parallax that allow for us to see, allow for us to determine distance because of slight differences in the image we're seeing. What they would do is they're like, let's just do that, but make a giant tube with extensions on the side. And then what they would do is there'd be prisms that would go back to your eyes, and so that you could really see see how far away objects are. And so so that these range finders, and they became huge, like they would be like longer than I am tall. That's all they used though. And then they would shoot and be like, we missed, lower it, shoot, oh, we missed again, go up. And then they basically would look for the splashes, because the ships were so far away they could barely see them at times. They could only see the splashes from their shells. But so yeah, by the end of World War II, these fire control systems and all that math and applied physics that that was taken into account resulted in approximately 4 times increase in hit rate, even at night, which was also during there was a rainstorm as well during this time. So that's really all I've got for you. If anyone has any questions, the last thing I want to point out is that battleships are hopelessly obsolete and they are not used anymore. So big guns are a waste of time.
Thank you, Jared. We do have some questions for you. So reading from the question thing. So first one, does each individual shell cause a whiplash effect and move the boat when shot? And would this mean you can't fire more than 1 gun at a time?
No, so because the battleship itself weighs so much, and the water that it's sitting in also has a lot of mass, the ships actually really wouldn't move much when they fired. They were relatively stationary, and they didn't have to take that into account. That being said, they usually did not fire all the guns at one time because they wanted to, especially when they were trying to figure out their range before they had these fancy fire control systems and radar, which tracked the target. They had to do these bracketing shots, and so they'd fire one gun at a time. And the other thing is you have to take into account, even after you do all these corrections, sometimes one of your guns will always shoot low, and so you have to do a ballistics adjustment for that specific gun to correct for some systematic error that your computer is not accounting for. And the other thing is and then I missed many different things that they like. The other thing is the temperature of the gunpowder actually determines the final velocity of the shell, its final speed as it leaves and enters into the exterior ballistics as it travels through the air. And just to show like how much gunpowder these bad boys had in them. This explosion right here was from all that gunpowder blowing up after getting hit. So no one survived on that ship out of a crew of 1,200. And during that battle, that happened to 3 British battle cruisers. And no joke, after the second one exploded, this one, the commander of the British battle cruisers turned around and said, "There's something wrong with our bloody ships today." Anyways, yeah, that's funny. Okay, that was a long answer for a short question.
No, that's good. We're learning a lot. There's another question which just says, range is varied as in targeted range plus or minus 15,000 yards.
Oh, I'm sorry. So basically from like 5,000 to a maximum of 15,000 yards. So the Battle of Jutland was anywhere from like 5,000 to 15,000. It's actually a chaos. It was like a disjointed set of like 4 different battles. Really was chaos. It's very fascinating. There's a very good video, like 20-minute long animated video on YouTube if you're curious.
Does anyone else have questions for Jared?
Yes, I have a question.
Go ahead.
So I was wondering, do you have any investigation of the design of the battleship armor? Because as far as I know, that the thickness and the angle of armor of a battleship is different at different places. So it depends. I mean, it's very important because it decides what is the most effective incoming angle for shell. So do you have any investigation of this part?
So that is a little bit beyond what I was talking, but it does kind of get into as you fire further. So at short range, your rounds are coming in effectively horizontally. But once you start firing at long range, so many miles, it's what they would refer to as plunging fire. Or you could point your guns up really high and fire plunging, which is what they did to the Bismarck. What they did is they had 2 ships that fired point blank range, and they had the other one that did lobbing fire until the Bismarck, which was a German battleship, just stopped shooting. But as for armor, and actually, if you're curious, we can talk about it later. So there's a ton of things that went into deciding battleship armor. There would be an armored belt, which is like 12 inches or more of just steel along the water line, which is where the hole in the water actually meet. And the idea was that would protect from this direct fire or even from plunging fire, from basically the giant shells from punching holes through the ship at the water line to prevent flooding. But you also had armored deck systems, which were set up in multiple layers, where they would have one layer that would help bust. Let me go back. This cap right here. So this shell is just like a giant chunk of steel with a penetrating cap on top. And so if you can disable that penetrating cap, it decreases the effectiveness of the shell. So like battleship armor towards the end, by the time World War II came around, the deck armor, which protected from plunging fire, had this cap armor. So it would try to deform the penetrating cap. And then it would have the main armor, which was like 4 or 5 inches thick. And then the idea was that would decrease the penetration. And then there was below that a splinter deck or a spalling deck, which would protect the decks below from splinters and chunks of the blown up armored deck raining down onto it and penetrating. And so in the way that they designed the armor layout, is the idea is they would, this is the last thing I'll point on. There's tons of stuff. I'm more than happy to talk for hours about it, but they would design the ship. But what they would do is they'd have a centered armored citadel where they'd have these massive armored bulkheads lining up with the armored decks above, the keel at the bottom, which is the backbone of a ship, and then the armored belts on the side. And then they'd have, and this would include all of the machinery would be located in this area, all of the radar, fire control, and the main guns. And the idea was that this armored citadel, which is only about half the length of this ship, has enough buoyancy to keep the ship afloat if everything else is flooded. And that's the area that's protected. And so there were a lot of things that were developed, and the Battle of Jutland changed a lot of people's views on things and showed that speed doesn't save you, which is what the British found out the hard way. That's why so many other ships blew up. They had like their battle cruisers had very little armor and they relied on speed, and which is okay if you use a battle cruiser the way it was supposed to be used. But when you use it as a battleship, well, you lose 3 of them and 4,000 people die, which was a national embarrassment. There's many things that went into developing these battleships, the armor for the battleships.
Well, it is 5 p.m. and as we said before, if you would like to ask any more questions, you can reach out to our group and we can put you in touch with the speakers, or you can just go to the speakers yourself if you know them. But thank you so much to everyone for coming. I think this went really well for the first time. Yeah, thank you.
Thank you, everyone.